Well, we have more stuff on friction, and then we're going to do some practice problems. I think there's time for that. Not too many slides left. Or are there? Yeah, if you have your homework for last week to turn in. Classic problem, yes. So yesterday we were looking at this notion of friction, and we're looking at a few different problems, like whether a box is going to slip, or if it's going to tip, or what is the minimum force for impending motion, and you have to consider whether the box could tip or slip. It's sort of a call box. And starting with impending motion at one point, you can kind of think about the force that would be required to keep a crate from sliding down a slope compared to the force required to make the crate slide up this slope, which is a lot bigger. So that's when there is impending motion at one point. But some systems, if something's going to move, it's going to move at multiple points. And each one of those points could have different coefficients of friction, like you got a brick surface here, maybe a cement surface there. So, but the brick maybe, I don't know, so the coefficient of friction is less on the brick than it is on the cement. Well, you got these maybe rubber stoppers here too. So anyway, the point is they can be different. And this question, I'm not sure this is worded properly. Let's think this through. What is the maximum angle for stability? And I think the maximum angle for stability is 90 degrees. What they really are meaning is the minimum angle for stability, where it's going to slide down. Because if you're at 90 degrees and you go more than 90 degrees, you're going to fall backwards. That's not the problem that we're interested in. We want to know what is the minimum angle for stability. Right, because you can commit yourself, if the ladder's like this and you step on it, it's just going to collapse the rest of the way down, right? So when you think about this, when the ladder moves, it's going to slip at A and B, right? So and at the limit, again, so basically we have to be, if it's slipping at A or B, A and B, and so we basically are going to assume that we are at the maximum friction force at A, which is going to be 0.3 times the normal force at A, and we are at the maximum friction force at B, which is going to be 0.2 times the normal force at B. Right, that's kind of the assumption. If it's starting to slip, both of those points are going to be at their maximum friction values. Sometimes I wonder, well, is it true? Could it just be at the limit of one and not at the other? But if it's slipping, they both kind of have to be at their limit. Knowing that allows us to solve for the equilibrium equations that are going to get us to that point. Well, before we do that, we're going to draw the forces on here. So they're going to have this normal force at A. And yeah, and so again, thinking about the impending motion, if it's going to slip, the ladder is going to slip out from under the person. So motion is going to be, the top is going to come down, and the bottom is going to slide out, right? That's the way the motion is going to actually happen if it happens. We want to know what's the limit, you know, the smallest angle we can have and still be stable. So friction is going to be pointing this way, our FA. And our FB is going to be pointing up. It's going to be trying to keep that person falling. Our NB is going to the right. So if the ladder is 10 feet long, then what is the height of NB? Yeah, 10 sine of theta. You read that? Hopefully. And the distance here is going to be 10 cosine of theta. Okay, so the sum of the fx's equals 0, and that means we're going to have NB minus FA. And that's really convenient because if FA is at its limit, then that means NB can be replaced by 0.3 times NA. That removes one of the unknowns. Sum of the Fy's is 0 is going to be the NA going up minus, well, I'm sorry, plus FB because FB is going up minus the weight of the person. And we don't even know the weight, but we're going to just put a W here. And kind of massaging this a little bit. So if FB is 0.2 times NB and NB is 0.3 times NA, you can write this as NA plus 0.2 times 0.3 times NA minus W, which is very convenient. So therefore, W is going to have to equal 1.06 times NA. So this is helping us reduce some unknowns, right? And have fewer unknowns. And now we're going to do the sum of the moments, say at B. So that's going to equal NA times 10 cosine of theta. Minus FB times 10 sine of theta. Nope, let me see. It's actually FA minus FA times 10 sine of theta. And then there's this W, which is going to be minus W times 3. And I'm going to try to squeeze it in there. Minus W times 3. Okay, and this has an angle in it, which is helpful. So, so we can actually say, all right, so 0 is going to equal an A times 10 cosine of theta minus 0.3 NA times 10 sine of theta minus 3.18 times NA. And the NAs cancel out. Doesn't really matter what the weight of the person is. What really matters is that 10 times the cosine of theta minus 3 times the sine of theta has to equal 3.18. How do we solve something like that? You get an equation like that, what are you going to do? Try a trig identity? What if you only have 1 minute left to go on the test and you didn't bring a cheat sheet with all the trig identities? What would you do? What's the Hail Mary? What would you do? Sorry? You might think of that dividing by sine of theta, then you get cotangent, but then you're going to get 1 over the, yeah, no, doesn't really help. You know what you're going to do? You're going to guess and check. Yep. And just keep, first, yeah, just keep going like in every maybe, 30 degrees, try a different angle and see what happens. And then, where it changes from positive to negative, the equation here. Well, if you something like that equals 0, you're trying to find the zeros of this equation, right? What angles of theta is going to give you a 0. And now I suppose, let me see, is it possible to maybe make a substitution where, I mean, can't we say that, cosine of theta is going to be the square root of 1 minus sine squared of theta? So you could put everything in terms of sine theta, and maybe if you square that, but you're still going to get these weird cross terms, right? I don't think you're going to get a really clean thing. But if you could substitute out maybe sine theta, you might be able to find the 0 easier that way, but it's still going to be very nonlinear and messy. So you're still going to need to guess and check. I think it comes out to guess and check. You can write a computer program to just change theta by in steps of 1 degree until you find, do some MATLAB real easily. Be a good MATLAB problem to kind of look at. But ultimately, you're going to find that theta equals 55.6 degrees. And you might actually write here something like guess and check as one possible approach to solving that. And then you have the situation where you have impending motion at some points. And that's where you have situations where, what force is needed for motion, and will block C slide? There's a few scenarios you have to kind of think about, right? Either block C is going to slide with block B, or it's going to remain stationary. Block B is going to slide out between those two, right? Block A is anchored, but block C is just kind of floating. So it's kind of annoying, but you got to consider alternate scenarios. Figure out based on mathematics which one is going to happen. So they're telling us the blocks weigh 20 newtons and the friction coefficient is 0.25 between each surface. So you can start with case 1, and that's where where B slips at both surfaces. You got to draw the free body diagram, right? So you got to draw the diagram of block A, which has its weight and a tension force acting on it and a friction force. So block A is not going to move. But it's feeling a pull because if we're tugging on block B, it's going to want to be moving away from the wall. Right? Can you visualize that? And TA is going to be, there's going to be a little tension in that rope because the friction force is pulling that thing away. Now B is it's going to be experiencing a normal force from above, which is an opposite of the normal force that block A was feeling from block B, right? Those are flipped. And we're pulling on it this way. Motion is this way. So friction is opposing that, and it also has to be the opposite of what it has shown on the other block. So FAB is opposite of that. In addition to NAB, we've also got this is going to be sort of applied here. We've also got the block's own weight. So it's got there's more weight on the second boundary. And then we've got to have a normal force from B to C, hooking up. Any questions on those forces? Those are the forces. So they're pointing to the left on block B because block B is the one that's going to be slipping to the right. So they're opposing that motion. Normal forces are pretty explanatory. And now we can actually do the equations of equilibrium. So on block A, we're going to have the sum of the Fy's equal to 0. And that is going to equal NAB minus W sub A. And we know W sub A is 20 newtons, so NAB is going to be 20 newtons. Then we turn to block B, and the sum of the Y forces is going to be NBC minus NAB minus WB. So in that case, our normal force from below is going to be 40 newtons. So NBC is going to equal 40 newtons. NAB. And the sum of the Fx's, oops, that should be an X. is going to be P minus FAB minus FBC. Okay, but what are FAB and FBC? Well, if we're at impending motion, those forces are at their limits, right? And so FAB is going to equal mu times NAB, which is going to equal 5 newtons. So, and this is because of that. And also FBC equals mu times NBC, which is going to equal 10 newtons. And so adding those up, that tells us that P is going to equal 15 newtons. So that's the force that we would need to pull on the block if it was going to slip out between both of them. So who wants to place a bet? Do you think that's going to happen, or do you think it's more likely that it's going to slide with block C attached to it? Yeah, should we place bets? I don't know. Or does anyone make a forecast? Sorry? You think C will not move? Well, to find out, we're going to look at case 2 where B and C are going to slide together. Everyone ready to move on? So now we're going to have to consider those two blocks together. And the idea is consider that we start at P equals 0, in which case the blocks are in equilibrium. We know that, right? And then we're going to increase P until something happens. Until something happens. And the case with the lowest P is the one that occurs first. Now, I don't know. I sometimes wonder, does it matter how fast you're yanking on a thing? Remember those like magicians that would like yank out a tablecloth beneath a fully, fully set table of dinnerware, and it all stays in place? Whereas if they pull it out slowly, it would all fall on the ground, right? I don't know. Should ask Leela. Yeah, it's a physics problem. They should know that. I don't know if this is a similar situation. Probably not. But we're gonna kind of suss out this problem where the blocks are slipping together. So now we're going to have the same old A block with its TA and its NA. NAB. And it's FAB, whoops, FAB, wait, going the other way. Same as before, that block is the same. And then we're going to consider this whole thing as one unit. So the block BC is going to have a NAB going down on it. FAB, trying to keep it from moving to the right, it's going to have P applied at B. It's also going to have an FCD and an NCD. It's also going to have a total weight of WB plus WC. That's going to be providing the normal force reaction NCD. So this is, you know, right away you can kind of see, well, okay, the block's going to be heavier. So it looks like to me the FCD is going to be bigger on the bottom, right, than FAB was. So, or FBC. FCD is probably going to be bigger than FDC was in the previous example. So yeah, it probably is going to be the first case. And block A hasn't changed, so we could just say it's the same. So NAB is going to equal 20 newtons. And blocks B and C are going to have the same equation again. We're going to have, in this case, though, NCD going up minus NAB minus WB minus WC. And we know that, therefore, that's going to basically tell us that NCD is going to equal 60 newtons. Got 3 blocks of 20 newtons apiece on top of it. And the sum of the Fx is equal 0 is going to give us P minus FAB minus FCD. And, you know, at impending motion, FAB is going to equal mu times NAB, which is 5 newtons, like before. And FCD is mu times NCD, which is going to be 15 newtons. So this is telling us, in this case, P would have to be 20 newtons. So by exploring this, we've shown that it's going to be block B sliding first. And our total conclusion here block B slips when P equals 15 newtons. And C does not slide. So, any questions, comments on that? Does that seem plausible? Any questions? Moving on here. So what I thought was a short lecture actually has quite a bit involved slides. There's only about 3 more slides, 4 more slides. They've got a lot of writing on them. I was sort of thinking, maybe we should just stop. Maybe I should I'm just kind of thinking, you know, there's some good stuff here. But it'd be nice to do some of these before I let you go for the weekend. But then we won't be able to cover more of the advanced stuff. But I can kind of, maybe I should actually just go fast through this. They've got this this thing with wedge. Does your hand have a wedge thing on it? Yeah. So wedges are interesting devices. You know that they're doing. It's an example of mechanical advantage because the weight of the crate and the P is scaled. So this angle kind of helps that mechanical advantage going on. So you can keep that crate up with a much smaller amount than the weight by just using a smaller force P to keep the crate from pushing everything downwards. And sometimes you get the situation where P is less than 0, meaning it's self-locking for B moving to the left. Like you could just leave it, the wedge will hold it in place without having any extra force applied. The trick is if you think about the motion of the wedge, so if we're actually trying to find, you know, what is the minimum? If we're asked to find the minimum P to keep the crate from sliding down. The minimum P to keep the crate from sliding down, which way is motion? Yeah, that wedge is going to have to slide to the left, right? If the crate's going to push this thing down, that wedge is going to have to be popping out left, right? And this reminds me of my my central spine. I think I have a vertebrae that kind of went like, but your body can be wedges too. So this motion of the block wanting to go that way means that friction is going to be opposing it, right? So FAB is going to be trying to keep it in, right? Just like trying to keep that crate from sliding downhill in the yesterday's lecture. FBC is going to be also keeping that crate from popping out. It's going to resist the motion, right? Because if the wedge wants to slide to the left, friction is going to try to stop it. So it's a little bit, takes a little bit kind of working your head around this thing. And you have NAB from above and NBC from below, which are going to define those forces. You also have on this crate NAB here, and then FAB, which is going to be working to pull the crate away from the wall. You're going to have WA, and you're going to have an FA, and an NA. This is at all points, including this surface, this surface, this surface. We're assuming the bottom wedge is going to stay fixed. So there are 3 different friction forces involved here, and they're all going to be at their limits. For A, we're going to do the sum of the Fx equals 0 and the sum of the Fy equals 0. For B, we're going to do the same thing. And impending motion is meaning is going to tell us that FA is going to equal mu times NA, FAB is mu times NAB. FBC is going to be mu times NBC. So those are all at their limits. And that's 7 equations and 7 unknowns. As long as we're given W. So the unknowns are P, FA, NA, FAB, NAB, FBC, and NBC, all those 7 unknowns. But if you see that, it's the same kind of deal as the previous block. It's just, setting up those free body diagrams for each of those parts, and kind of grinding through the equations and then gradually eliminating unknowns. Okay, questions? You'd have to be given that.
What is it?
Oh, it's the weight of the crate, yeah. Yeah, they said the crate's 100 pounds or something. That's your W today. Mm-hmm. Okay, questions? So it's kind of a lot to squeeze in, but again, these are concepts, and we're going to look at belt friction in the homework. Belt friction is pretty straightforward. There's a fairly lengthy analysis you can do, but I just don't think it's worth the time it takes to do it. You can actually check the book. The takeaway, though, is that when you have, so this is a case where you've got a belt sliding over a drum, which can model a lot of other situations, a peg. They have a problem where, like, there's a woman holding a rope with a young boy dangling off the edge of a cliff. And there's that, the cliff edge is sort of like the belt friction formula, because the rope is kind of going over the edge of the cliff, and there's coefficient of friction between the rope and the cliff. And you can figure out, you know, how much, and if you consider the coefficient of friction between her shoes and the ground and her weight versus the boy's weight, whether the boy's going to fall or can be held or she can pull him up, you know, all those three situations. It's a fun kind of problem to explore. Once you learn these tools, you can do a lot of fun stuff like that. The formula for belt friction is very simply T2 equals T1 e to the mu b. But you got to figure out which way impending motion is. And in this case, they're showing you impending motion here. That's not b, by the way. That's mu. Well, that's T1 e to the mu, not mu sub b. It's mu times beta. And beta is this angle here. It's the angle between the two tangent points of the rope or the belt. And beta is in radians. And impending motion is that way. And since mu is positive, beta is positive, is T2 going to be bigger than T1 or smaller than T1? Bigger. Yeah, if you want this thing to slide, whoops, if you want this to slide towards this way, yeah, because of all the friction, you got to overcome all the opposing, these are all these little microscopic friction forces trying to prevent you from moving the belt that way. You got to overcome those as well as the T1 load itself, right? So that plus all those friction forces has to be factored into T2, and it's defined very well by this formula, T2 equals T1 e to the mu b, beta. And T2 is the side, you know, is on the side where the belt moves to it. Does that make sense? The belt moves to, I don't know if that makes sense. So the belt's moving towards side T2. Right, so try to think this through. So again, if you have like a figure here, a cliff, and this young, helpless young boy there, and she's trying to keep him from sliding down, right? If he weighs 100 pounds, and she's trying to prevent impending motion that way, which one is going to be T2? The boy side or the woman's side? Yeah, the boy side is going to be T2, right? On the other hand, if she's trying to pull him up, then she's on the T2 side. She's got to do a lot more force than the 100 pounds to pull him up, right? That makes sense? I love these life and death situations. Helps clarify everything. And T2 is always bigger than T1. We don't have any problems involving pulley friction, just more formulas. It's interesting because it's sort of, again, it's sort of looking at the micro level or something, you know, where those two, where the axle is kind of rubbing against the pulley. It's not rubbing all the way around there. It's only rubbing at a certain point based on the load on it. And And, you know, I've never done pulley friction. I've heard it's interesting. There's a formula for it in case you're interested. T is going to equal 980. Oh, this is because the block is 100 newtons, 100 kilograms. So it's going to 981 newtons times RP plus RF in case you're interested over RP minus RF. Where RP is the radius of the pulley. Wait, where's RP? There's RF, and there's RP. Yeah, anyway, I don't know enough to know. So I see an RF, but I don't see an RP. So that might be the, oops. That might be this R here. Maybe it's the radius of the shaft. Anyway. And you can get these complicated systems now where you start to factor in all these things, right? So if you've got a block and now you've got a peg here, you've got a pulley, you can start figuring out all these friction forces needed you have to overcome to get this thing to move. And this is just sort of adding additional force. You can figure out, you can sort of start here, you know, and whether block B or tips. That's another scenario. Wow, look at that. Could block be tip? Yeah, it could tip because you're going to get a moment there, right? If it's attached way up at the end there, and you're getting a friction force like that working on it, yeah, that could happen. All right. Well, I think that's enough. I think let's take a second here and kind of look at what's coming. I must put a note to myself next time. Let's go to modules here. I'm wondering if what we might do this week, because it's a little bit different. You like to have those practice problem sessions, right? Doesn't that help a lot? I'm afraid if we don't do that, then chances are there's going to be less understanding. I don't know. What do you think? So this is friction. I think I made notes to myself. I should have read this. I usually do this. Let me see what it says. Problem session. This week we do a review for test 3 on Monday, test 3 on Tuesday, and then we should have a Q&A on homework 11 on Wednesday before doing friction 1 on Thursday. Homework 11. But we did homework 11. Q&A. I used to do Q&A sessions as well, but this is actually an old note here. So this is my suggestion that we did, and this is kind of what we did. Oh, and we're only supposed to do friction 1 lecture this week, I guess. But point is, we're kind of slipping. And why don't we, yeah, and so then I think we started a centroid lecture. And maybe this will actually work out well. So but what we could do is maybe have, what I think would be good is if you could try tackling, would this make sense to tackle some of the problems that are the relatively simple ones? Let's look at the homework and see what that is. And here's the problem session. So this one and these two should be doable. This one could be probably something we explore in a problem session maybe on Monday. What do you think about that? And so we don't have this due until, in fact, is there a due date on this thing? Let's see. Friction. Let's go to the next guy here. So this says it's due November 18th, which is, yeah, I think it's built in already that we have this extra time to work on friction. So actually there's nothing due on Sunday. You get a little break. Although maybe I could put a quiz together. No. I think we're supposed to have a quiz 6 this weekend. Since you're not having homework due, what do you think? It's not bad. 4 problems. Otherwise, it piles up. Quiz 6 would be on, let's see, it would be on internal forces, I think. Right. Is that it? No one's going to give me anything on that. I don't know. I'm trying to work this out. What do you think? Quiz 6? It's not more work. I'm giving you a what's that called? A furlough. I'm in that state, that wonderful state of not knowing. The teacher doesn't always know. So I'm going to have to make a better set of notes for it. But looking ahead here, let's sort of get the big picture here. So, so what we sort of have here, week 12. Actually, no, I have quiz 6 is set up for week 13. I think the date needs to be adjusted on that too. We had quiz 5, right? Quiz 5 was already, that was there. So yeah, I think you sort of get a little holiday. I know you all need it. I certainly need it. So then we'll be doing some of the center of gravity and centroid. The question is whether one problem session is enough. Maybe we can get by with just one problem session, or if you need problem sessions, that can become friction. So I would love it if you could try tackling some of the easy friction problems. And maybe I'll just tell you, I'll send you an announcement of which ones you should do. And try tackling those before class on Monday. And then if you have any questions on those, we could talk about those. And then we'll tackle the more, the larger ones, which are the more involved ones, which I think it's important that we actually have some time to kind of work through some of that together. And just so, this one's probably not that hard. This one, we did one just like that in lecture yesterday. So you should be able to do those. That one, not very hard. This one's from today's lecture. But, if we just did like maybe the first 5, you just work on the first 5, try to knock those out. And then you get these sort of system ones. This one, well, that's not too hard. This one's a system because you're factoring in not only the fridge, but also the man, because he has friction between his shoes and the floor, and then you've got a wedge problem, and these things, I think it'd be kind of good to maybe tackle some of these in class together, because these are a little more involved. And then the infamous boy on a rope. Yeah, that's the only one really where we're using peg friction here. This is belt friction there, right? And so there's only 2 problems with belt friction, 1 wedge problem. Yeah. The question is, what force does she exert to let the boy descend at constant velocity? So we're not even considering her shoes. Some variations of the problem consider the friction between her shoes and the ground, and whether she can keep him, or whether she can pull him all the way up, or whether she can keep him from falling, that sort of thing. It was a lot of fun. Did you ever do the one with the clown? I saw this. I used to use this in my status class. Then I saw it in your physics textbook. The one where the clown. Let's see. It's a hilarious problem. There's a clown with a rope that goes to a pulley, and it comes around to another pulley and around to another pulley, and then attaches to his legs. And the question is, how much force does a clown need to apply to pull his legs out from under himself? Yeah, that's a fun one. Okay, so you all know what you're doing, right? No quiz, just work on the first 5 problems in friction. Thank you. Here. Oh yeah, and don't forget to turn in your homework if you haven't yet. Yep.